Imagine a bundle of 100 billion electrons squeezed into a sphere only 1 micron wide. According to the standard laws of physics we learn in school, this shouldn't exist. Those electrons carry the same negative charge, and they should repel each other with such violence that the whole cluster would vanish in a fraction of a nanosecond. Yet, in the late 1970s and 80s, an experimentalist named Ken Shoulders claimed to have discovered these stable clusters of charge, which he called electrum validium, or EVs. He described them as a new state of matter, something between chemical and nuclear energy levels. And his work suggests we might be missing a fundamental piece of how the vacuum of space actually works.
It sounds like science fiction because it challenges the fundamental space charge law. Shoulders was not a traditional academic. He operated more like a Renaissance inventor, supported by private patronage. His book, which was kept secret for 7 years before its 1987 publication, details how he moved away from massive, multi-million-dollar particle accelerators to do what he called garage-level science. He found that these intense charge bundles were hiding in plain sight within the plasma trash of almost every common spark discharge. He didn't need a super collider to find them. He just needed to look closer at the strike marks on his electrodes.
That's a bold claim, saying that the entire physics community just missed a stable entity hiding in every spark plug and relay switch since the dawn of electronics. If these things are as powerful as he says, why was he the one to find them? It feels more like he was misinterpreting common plasma effects or cathode spots that researchers have studied for a century.
He actually addressed that head-on. He admitted feeling humiliated when he looked back at the literature and saw the same strike marks in papers from the 1950s. The difference was that earlier researchers dismissed them as random damage or splattered material. Shoulders used a scanning electron microscope to prove these marks were not random. They were precise, circular craters or beads, often forming long chains. He developed a witness plate technique using thin foils of metal like titanium or brass. When an EV struck, it didn't just heat the metal, it left a signature that looked like a milk splash frozen in time. The consistency of the size, always around 1 micrometer, suggested this was a quantized, self-organizing structure, not just a messy explosion.
This is where the theory gets provocative. Shoulders collaborated with theoretical physicist Hal Puthoff, and they proposed that the containment comes from the vacuum itself. Specifically, they pointed to zero-point energy fluctuations. The idea is that the EV acts as a spherical monopole oscillator. By vibrating at specific high frequencies, it couples with the zero-point fluctuations of the electromagnetic vacuum. This creates a dynamic pressure that pushes inward, overcoming the mutual repulsion of the electrons. It turns the vacuum into a polarizable medium that functions as an unseen container. If this is true, Shoulders wasn't just finding a new particle, he was finding a way to tap into the background energy of space to hold matter together.
That leap to zero-point energy feels like a convenient way to bypass the fact that the physics shouldn't work. It's much easier to invoke an exotic vacuum energy than to prove a new law of electrostatics. Let's look at the actual behavior of these things. Shoulders mentioned something called a black EV. If these are intense clusters of electrons, they should be emitting light and ionizing everything in their path. How can something that energetic go dark?
The black EV is one of the most interesting observations in his notes. Normally, an EV traveling through a low-pressure gas like xenon creates a visible streamer because it's shedding electrons and ionizing the gas. But Shoulders found that under certain conditions, the visual trail vanished. The entity was still there because it would eventually hit a target and leave a massive strike mark, but it moved through the gas without creating light or ions. He theorized that in this state, the EV reaches a high-velocity equilibrium where its external fields are so tightly coupled or shielded that it doesn't interact with the surrounding gas molecules. It's as if it becomes a soft boundary that sweeps molecules aside without exciting them. It challenges the idea that a high-charge entity must always be a violent glowing plasma.
The technical breakdown of his experiments often involves these things boring through solid materials. He describes EVs drilling clean holes through aluminum oxide ceramic, which is a very tough refractory material. If this is a simple thermal process, the hole should look melted and irregular, but his descriptions suggest something more like a mechanical reamer.
That's exactly what the SEM photos showed. When he launched an EV into a tiny channel between two lapped ceramic plates, it didn't just melt a path, it bored a hole with a constant diameter, often around 20 micrometers, and it moved material in the forward direction. He called this momentum transfer. The EV seems to act as a complex engine. It doesn't wait for the material to vaporize. It appears to use radiation pressure to yank the material out. He even observed that if the guide channel was slightly larger than the EV, there was no damage, but if it was just a few percent too small, the EV would bore its way through with catastrophic force. This stiffness suggests the internal radiation energy density of the container is massive.
Let's talk about the hardware he used to see these things. He couldn't just use a standard oscilloscope because the events were happening in the picosecond range. He had to build a pinhole electron camera. How does that work in the context of something as small as an EV?
He designed a very simple but effective system. It used a tiny pinhole, about 0.06 millimeters, to project an image of the electron emission onto a channel plate electron multiplier and a phosphor screen. By placing the nose of this camera within a quarter-inch of his EV source, he could watch the EVs in flight. He saw them as burning embers shedding electrons. He even performed energy analysis by applying a deflection voltage. The results were surprising. The electrons coming off the EV weren't just a random spread of energies, they were often in a narrow band around 2 kilovolts. This suggested the potential well of the EV has a specific depth. He was essentially looking at the internal structure of a lightning bolt at a microscopic scale.
But the data seems to have a lot of variability. In his chapter on traveling waves, he admits that while he got a device to work the first time, repeating the results was a nightmare. He spent weeks changing gas pressures and pulse widths, only to get inconsistent output. If this is a fundamental discovery, shouldn't it be more predictable? The lack of repeatability is usually a sign that you're chasing an artifact of the experimental setup, not a new law of nature.
He was very open about those struggles. He attributed the difficulty to the fact that an EOV is a periodic structure, a chain of beads. When you try to run that chain past a periodic structure like a delay line or a helix, you're dealing with coherent interactions. If the spacing of the beads doesn't perfectly match the frequency of the circuit, you get destructive interference. He was trying to build a traveling wave tube where the beam was not a steady stream of electrons, but a train of these fierce charge bundles. He eventually realized that he lacked the microfabrication technology to control the bead spacing at that time. He was working with hand-wound coils and glass tubes, when he really needed photolithography and thin-film circuits.
There's also the issue of X-rays. Shoulders claimed that when an EV hits a low inductance target, it releases a burst of X-rays so intense it could ruin digital voltmeters several feet away. He even captured these strikes on X-ray film behind LED filters. If these EVs are generated in common electrical arcs, why aren't we seeing X-ray hazards everywhere? That seems like a major safety implication that would have been noticed long ago. Looking at the legacy of this work, Shoulders suggests that EVs could be used for super bright cathodes in displays, or even as the basis for a self-organizing artificial intelligence. That seems like an enormous leap from a micrometer-sized spark. If these things are so difficult to control and so prone to exploding or boring through their containers, how do they become a useful technology?
He viewed the EV as a new substance, a building block. Because they exhibit coupling behavior, meaning one EV can trigger the birth of another, or two can consort and travel in a synchronized pair, he saw them as being capable of forming vast, complex organisms. He imagined using deflection switches, similar to how we use transistors, but operating at sub-picosecond speeds. The power levels are the main hurdle. A single bead carries so much charge that it would blow a modern semiconductor to bits. But if you move toward current steering logic or superconductive circuits, the EV could theoretically process information at rates that dwarf current silicon technology. He wasn't thinking about a better transistor. He was thinking about an entirely new realm of electronics that he called the turbulent regime.
Despite all the detailed notes and the SEM photos, Shoulders' work remains on the fringes of mainstream physics. It hasn't been integrated into textbooks. Is that because the work was flawed, or is it the typical resistance to a paradigm shift that involves something as controversial as zero-point energy?
It's likely a mix of both. Science usually requires a level of mathematical rigor that Shoulders explicitly avoided. He stated in his preface that he didn't think or write mathematically. For a theoretical physicist, that makes his work hard to digest. Furthermore, the private nature of his funding through Jupiter Technologies meant that he didn't have to go through the peer review process that standardizes discoveries. But the physical evidence, the strike marks, the bored channels in ceramics, the X-ray film, that's harder to dismiss. Whether his zero-point energy explanation is right or not, he documented a physical phenomenon that produces charge densities and energy effects far beyond what standard plasma models predict.
The story of Ken Shoulders and the discovery of electrum validium serves as a reminder that even in a field as established as electromagnetism, there may still be fundamental surprises waiting in the small, messy corners of a laboratory. If these intense bundles of charge truly tap into the fluctuations of the vacuum, our understanding of energy and matter is only scratching the surface. It's a journey from the visible spark to an invisible electronic wilderness that challenges our most basic assumptions about how electrons behave when they are pushed to the limit. Sharing this exploration of the fringes of physics helps keep the spirit of discovery alive for others.
Imagine a physical entity so dense with electrons that it mimics the properties of a solid, yet it flows like a fluid and behaves like a single, giant subatomic particle. This isn't science fiction. It was the life's work of Kenneth Shoulders, an experimental physicist often called the father of vacuum microelectronics. Shoulders discovered what he called electrum validium, or more simply, EVs. These are high-density charge clusters, tiny bundles containing upwards of 100 billion electrons, packed into a space just a few micrometers wide. Now, the paradox here is immediate. Electrons hate each other. They're all negatively charged, so they should fly apart instantly due to Coulomb repulsion. But in an EV, they don't. They stick together in a stable, high-energy state. However, that stability is fragile. Shoulders found that when these clusters collapse or strike a target, they don't just disappear. They release a sudden, violent burst of high-energy X-rays. It's a specific kind of physics failure mode, and understanding it requires looking at a factor that most people overlook: target inductance. It turns out that the way we catch these clusters, the electrical drain they hit, dictates whether they vanish quietly or explode with dangerous radiation. Part 1. The discovery of the strong electron. To understand why these things emit X-rays, we have to understand what they are. Ken Shoulders wasn't a fringe theorist. He was a powerhouse at SRI International and MIT, the man who helped us give electron beam lithography. In the 1980s, while studying vacuum discharges, he noticed these consistent, microscopic craters left on anodes. They weren't random burns. They were precise, circular pits that looked like they'd been bored by a solid object. He eventually realized he was seeing the impact of condensed charge, clusters of electrons that had somehow overcome their mutual repulsion. He named them electrum validium, Latin for strong electron. These EVs are essentially non-neutral plasmoids. Think of them as a spherical monopole oscillator. While a normal electron beam spreads out, an EV stays tight, traveling at about the 1/10 of the speed of light. Shoulders hypothesized that they were held together by a balance of forces, possibly involving the potentum, or the zero-point vacuum. But the practical reality was that they acted as a single, massive charge. They are so dense that their current density reaches about 600 billion amps per cubic centimeter. That is an astronomical amount of power packed into a speck of dust. But this density is exactly what makes them dangerous. When an EV is moving, it's a stable soliton, but when it stops, all that potential energy has to go somewhere. Part 2. The X-ray release and the inductance factor. This brings us to the core of the mystery, the X-ray emission. Shoulders documented that when an EV is destroyed, it produces soft X-rays with energies around 2,000 electron volts. But the intensity and hardness of these X-rays aren't fixed. He discovered that the collapse is governed by the inductance of the target circuit. In basic electronics, inductance is the property of a conductor that opposes changes in current. If you have a high inductance target, say a long wire or a coil, the current from the EV impact can't dump into the ground instantly. The inductance chokes the flow, slowing down the dissipation of energy. This actually cushions the EV's death. But if the EV is caught in a low inductance circuit, a very short direct path to ground, the energy release is near instantaneous. It's like the difference between landing on a mattress and landing on concrete. In a low-inductance physics failure mode, the EV collapses so rapidly that the deceleration of billions of electrons happens in picoseconds. This extreme deceleration triggers what's known as bremsstrahlung, or braking radiation. Because the electrons are packed so tightly and stopping so fast, they shed their kinetic energy as high-frequency photons, X-rays. Shoulders realized that by controlling the inductance of the target, he could actually tune the radiation output. High inductance meant less radiation and more thermal work, while low inductance created a literal X-ray flashbulb. Part 3. Cultural Impact and the Legacy of the EV. The implications of this discovery were and still are staggering. Shoulders believed that the energy released during an EV collapse wasn't just kinetic. He saw evidence of nuclear transmutations. He observed that when EVs hit a target, they could actually reorganize atomic nuclei, turning radioactive isotopes into stable ones at room temperature. He called this plasma-injected transmutation. This suggests a world where we could neutralize nuclear waste using nothing more than precisely controlled electron clusters. Yet, despite Shoulders' pedigree and his 5 U.S. patents on the technology, this work remains on the fringes of mainstream physics. It challenges the Standard Model's view of electron repulsion. Because the phenomenon is so tied to failure modes, the destruction of the cluster, it's difficult to study without specialized high-speed equipment. Most labs see these discharges as noise or equipment failure, rather than a new state of matter. Shoulders' legacy is a reminder that some of the most profound physics are hidden in the moments when systems break down. The X-rays weren't just a hazard, they were a signal of a deeper, condensed matter reality that we are only beginning to grasp. Whether it's the key to clean energy or just a fascinating quirk of vacuum electronics, the strong electron forces us to reconsider how much energy is really hiding in the empty spaces of a vacuum.
Space is often described as a void, a silent emptiness between the stars. But modern physics suggests the exact opposite. If you look closely enough at what we call a vacuum, you find a seething cauldron of activity. Virtual particles are popping in and out of existence, and fields are vibrating with a minimum residual energy that never goes away, even at absolute zero. This is the zero-point energy, and some believe it is an infinite, untapped reservoir. Today, we are looking at the audacious idea of tapping into that quantum vacuum for power and a specific theoretical concept that might be the key to it all, something called strong electrons.
It is a fascinating intersection of established science and very speculative engineering. To understand the potential here, we have to start with the vacuum itself. In classical physics, a vacuum is just empty space. But quantum mechanics, specifically through the Heisenberg uncertainty principle, tells us that you can't have a state of absolute zero energy. There's always a baseline fluctuation. Every cubic centimeter of empty space is filled with these electromagnetic fluctuations of the zero-point field. The scale of this energy is where things get controversial. I've seen calculations suggesting that a coffee cup's worth of empty space contains enough energy to boil all the Earth's oceans. If that's even remotely true, why aren't we using it? Why is it considered untapped?
The challenge is that this energy is uniform and omnipresent. It's like being in the middle of a vast, perfectly calm ocean. There's plenty of potential energy there, but without a gradient, without a high point and a low point, you can't make it flow to do work. To extract energy from the vacuum, you have to find a way to create an asymmetry. You have to perturb that ground state. This is where the concept of strong electrons, or electrum validum, comes into play.
Strong electrons. That sounds like something out of a comic book. Is this a recognized term in mainstream physics, or are we venturing into the fringes here?
It's a bit of both, depending on the context. In condensed matter physics, researchers do talk about strongly correlated electrons. These are systems where electrons don't just act like a gas of independent particles, they interact so intensely that they move in a collective goop-like way. This behavior drives exotic phenomena like high-temperature superconductivity. But when we talk about strong electrons in the context of vacuum energy extraction, we're often referring to the work of Ken Shoulders. He used the term electrum validium to describe tightly bound clusters of electrons that he observed in high-energy discharges. He believed these clusters were held together by some force that countered their natural electrostatic repulsion.
Wait, electrons have the same negative charge. They should fly apart. If they're staying together in a tight cluster, something massive must be pinning them there. Are you saying the vacuum itself is providing that glue?
That was the hypothesis. Shoulders and later researchers like Hel Puthoff suggested that if you get enough electrons close enough together, they might interact with the zero-point field in a way that creates a localized dip in the vacuum energy. Essentially, the vacuum pressure on the outside of the cluster becomes greater than the pressure on the inside, pushing them together. It's an atomic scale version of the Casimir effect.
The Casimir effect is a proven phenomenon, right? Two metal plates in a vacuum getting pushed together because there's more stuff happening outside them than in the narrow gap between them. So the theory is that these strong electrons are basically a self-assembling Casimir system.
Exactly. If these clusters can exist, they represent a state where matter is deeply coupled to the vacuum's energy. Shoulders claimed these EVs, or electrum validium, could bore through solid materials and release far more energy upon impact than it took to create them. That's the tapping into the infinite part. The idea is that the cluster is a catalyst that coaxes the vacuum into a lower energy state, releasing that excess as heat or radiation.
If this is possible, it would rewrite everything we know about thermodynamics. But is it actually happening? Because it sounds a lot like a perpetual motion machine, which usually triggers a lot of red flags in the scientific community.
The skepticism is well-earned. Critics, like the physicist Massimo Pigliucci, have argued that many of these proposals violate the second law of thermodynamics. The second law says you can't extract work from a system in thermal equilibrium without a colder reservoir to dump waste heat into. Since the vacuum is the ultimate ground state, there's nowhere lower for that energy to go. However, proponents like Puthoff argue that the vacuum isn't a traditional thermal bath. It's a dynamic medium. They point to the Lamb shift, a tiny energy difference in hydrogen atoms, as proof that electrons are constantly exchanging energy with the vacuum. To them, the vacuum is a secondary reservoir we can cycle energy through.
So the Lamb shift shows the vacuum is active, and the Casimir effect shows it can exert force. But there's a huge leap between a tiny shift in a hydrogen atom and a vacuum battery powering a city. Is there any recent evidence that we're getting closer to that leap?
There was a very intriguing development in 2023. Researchers at Tohoku University and other institutions performed experiments involving something called quantum energy teleportation. Now, the name is a bit of a misnomer. They aren't zapping energy across space like Star Trek. Instead, they use the fact that different parts of the quantum vacuum are entangled. By spending energy to gain information about the fluctuations in one spot, they could use that information to catch the right fluctuation in another spot and extract energy there.
Wait, you said they had to spend energy to get the information. Does that mean the net energy gain is still zero, or are they actually coming out ahead?
In those specific experiments, the total energy of the whole system is conserved. You aren't getting something for nothing. You're effectively borrowing energy from one location and making it available in another by using quantum entanglement as a bridge. It doesn't provide a way to mine the infinite vacuum for free power yet, but it proves that you can technically extract energy from a local vacuum state that was previously thought to be inaccessible.
It feels like we're splitting hairs. If we can't get a net gain, then the vacuum isn't a power source. It's just a very strange, very inefficient battery. What about the people like Garrett Model or Hal Puthoff who are looking for a way to actually generate power?
They're looking at more mechanical or chemical
approaches. One concept involves pumping gas through Casimir cavities, basically incredibly tiny gaps. The theory is that as the atoms enter the cavity, their electron orbitals shrink because the vacuum energy inside the gap is lower. This shrinkage should release a photon, energy we can capture. Then, when the atom leaves the cavity, the ambient vacuum fluctuations re-energize it. If you cycle the gas, you have a continuous flow of energy. Model has published papers on this, and while the power levels are extremely low, the results are, as he puts it, tantalizing but inconclusive.
That word, inconclusive, is doing a lot of heavy lifting. If the physics were solid, wouldn't we see a clear signal? Why is it so hard to verify?
Because the energy density might be huge, but our ability to interact with it is incredibly weak. It's like trying to catch a hurricane in a butterfly net. Also, there's a massive problem with the math. This is known as the cosmological constant problem. If you take the energy density of the vacuum predicted by quantum field theory literally, the universe should have curled up into a tiny ball long ago because of the sheer gravitational weight of all that energy. But we see a universe that is expanding. There's a discrepancy of about 120 orders of magnitude between theory and observation. One of them is fundamentally wrong, and until we know which one, we're building engines on a foundation we don't fully understand.
That's a terrifying margin of error. 120 orders of magnitude is the difference between an atom and the entire observable universe. If the vacuum energy is that much lower than we think, then maybe there's nothing to tap into at all.
That's the standard view. Most physicists believe the zero-point energy is just a mathematical baseline that cancels out in almost every interaction. But then you have those strong electrons again. If certain conditions like specific geometries or high-density plasmas can amplify these effects, the rules might change. This is what Nassim Haramein and others call space-time metric engineering. They aren't just looking for a new fuel. They're looking for a way to manipulate the fabric of reality itself to generate propulsion or power.
You mentioned propulsion. I've heard rumors about NASA's Breakthrough Propulsion Physics project looking into this. Is the vacuum the key to interstellar travel?
The idea is called a propellantless thruster. If you can push against the quantum vacuum instead of carrying heavy rocket fuel, you can theoretically accelerate indefinitely. There were experiments like the M-Drive that claimed to do this, but later rigorous testing by groups like Dresden University suggested the thrust was actually caused by mundane things like magnetic interference or thermal expansion. However, the theoretical work continues because the payoff is so high. If we could tap into the vacuum, the rocket equation, which dictates that you need fuel to carry your fuel, simply disappears.
It seems like we're standing at a doorway where the hinges are made of high-level math, and the door itself might not even exist. On one hand, we have experiments proving the vacuum isn't empty. On the other, we have a total lack of any device that can even power a light bulb. Where does that leave the strong electrons concept?
It leaves it as a high-risk, high-reward frontier. The search for strong electrons is essentially a search for a new phase of matter, one that is so deeply intertwined with the vacuum that it breaks our current models of how particles behave. Whether Shoulders' observations were truly a new form of electron interaction or just a complex plasma effect is still debated. But the quest has pushed us to look at condensed matter in a new way. We're now finding direct evidence of strong electron correlations in 2D materials like magic angle graphene, which can switch from being an insulator to a superconductor with just a tiny change in voltage.
So even if we don't get infinite energy from the void, the attempt to find it is revealing new properties of the materials we already have.
Precisely. Science often works that way. The search for the Philosopher's Stone gave us chemistry. The search for the luminiferous ether gave us relativity. Even if the quantum vacuum isn't an infinite gas station, the techniques we developed to probe it, quantum entanglement, nanostructured Casimir cavities, strongly correlated electron systems, are the building blocks of the next technological revolution. We're learning how to engineer space and matter at a level where the distinction between them starts to blur.
It's a humbling thought. We might be swimming in an ocean of energy we can't see, or we might be chasing a phantom born of a math error. Either way, the vacuum isn't just nothing. It's a field of potential that is forcing us to rethink the very nature of what stuff is made of. The idea of tapping into the infinite is probably the most ambitious goal humanity has ever set, and whether it's through strong electrons or something else, the journey into the void is far from over.
It's about understanding the limits of the universe.
If we can find a single loophole in the second law of thermodynamics, or a way to harness the fluctuations of the zero-point field, we change the trajectory of our species. It's the difference between a civilization bound by scarcity and one that has truly unlocked the cosmos.
If you found this exploration of the quantum world as intriguing as we did, consider sharing this episode with someone who loves to ponder the mysteries of the universe.